Hello everyone. Good day, ladies and gentlemen. This is Razavi, Assistant Professor of Faculty of Engineering of University of Science Culture in Iran. The title of my presentation is Comparative Assessment of the Seismic Behavior of Reduced Core Length and Conventional Buckling-Restrained Bracing Systems, which is a part of a research project regarding improving resiliency of buckling-restrained braces. My co-authors in this paper are Milad Ehteshami and Dr. Imanpour, Assistant Professor of University of Alberta. First of all, we'll take a look on the table of contents: introduction of buckling-restrained braces, research motivation, case studies, nonlinear analysis and results, and finally the conclusions. As of the introduction, BRB systems are composed of encasing and steel core. The steel core is responsible for energy dissipation. The encasing is responsible for preventing the core from buckling. The comparison of BRB and conventional braces are shown in this slide. The conventional concentric braces perform well in tension, but they buckle in compression and give an unstable, non-symmetric hysteresis curve. In BRB systems, however, the compression and tension are somehow symmetric, which leads into wide sound hysteresis loop. The first Japan application of the BRB systems was in 1987 in Nippon Steel Headquarters No. 2, Tokyo. The qualification tests for these new braces was completed in 1987 and the installation was performed at the same year. Application of BRBs in US backs to Plants and Environmental Science University of California at Davis, 1999, and a rehabilitation and retrofit project in Bennett Ferrell Building with the application of total 344 BRBs in 2001. There is a good evidence of the BRB performance in past earthquake, which is a strong one happened in Japan named Tohoku 2011 with a magnitude of 8.9. The building supported by BRB was distanced from the epicenter 234 kilometers. The peak ductility of the BRB was 4 and the accumulated plastic strain was 20%, which shows the good performance of the BRB even in the strongest earthquakes. There are many alternatives for the encasing of the BRBs, such as conventional encasings which are filled with concrete or grout. Other types of encasings are composed of sandwiched prefabricated concrete blocks wrapped with CFRP layers, and other types of encasings are all steel encasings. The BRBs can be categorized to normal length, long BRBs, and short BRBs. The long BRBs in the form of triple truss confined BRBs are applied in megaframe structures and diagonal braces in long span spatial structures, which have shown good stable hysteresis curve and has satisfied the cumulative ductility provisions and also showed proper fatigue properties. Another type of BRBs are reduced length buckling restraint braces, denoted as RLBRB. These type of BRBs are composed of two parts: the short BRB, which experiences inelastic deformations, and an elastic part, which is composed of pipe or any other type and is going to remain elastic during the earthquake. This type of BRB has advantages such as stable and symmetric hysteresis curve, enhanced energy dissipation, and increased post-elastic stiffness. The test setup of the reduced length BRB in both uniaxial and subassemblage test setup can be observed in this slide, and the hysteresis loops of the reduced length BRB is shown in this slide. After the introduction, let's talk about the research motivation. There are advantages and disadvantages regarding the BRBs. The advantages of BRBs are wide asymmetric hysteresis loops and great energy dissipation. They possess high ductility and high ultimate displacement capacity. But on the other hand, the disadvantages of BRBs are low stiffness compared to CBF concentric bracing frames, low post-elastic stiffness and sensitivity to P delta effects, and relatively large residual drifts. Different methods have been proposed for improving the BRB defects. One of the methods for improving the performance of the BRBs is the dual system, which improves the over strength of the structure. And another method is reduced length BRBs, which improves the lateral post-elastic stiffness and shear capacity. The SMRF-BRB dual system is composed of two frames, BRB frame and the moment-resisting frame. The drift concentration in BRB systems can cause global instability caused by P delta effects and large residual drifts. Adding SMRF to BRB in the form of dual system can create positive global stiffness by secondary stiffness after the BRB. Here I'm going to describe the case studies. The data regarding the loading of the structure are presented in this slide. The loading and design are complete according to ASC 716 and ASC 360. As shown in the figures, there are two types of buildings, namely 4-story building and 9-story building. The structures are designed once with BRBF system and another time with reduced length BRB system. The braced frame bay is once designed with pinned beam-to-column connection and another time with moment-resisting connection. Therefore, a total of 8 structures are designed. In the 4-story building, a dual system composed of BRB and SMRF system is also designed to compare the effect of dual system. The SMRF-BRB dual frame system is designed according to ASC 7. While the moment-resisting frame is capable of withstanding 25% of the total base shear, the moment frame is considered to be placed between the two BRB frames, as can be seen in this picture. The procedure includes designing the displacement control elements and force control elements. In the first step, the BRBs are designed for the applicable building cold load combinations. In the second step, the force control elements such as beams and columns are designed for the expected forces resulting from the yielding of the braced cores. The expected forces are calculated according to the figure shown in this slide. In this slide, the design results are presented. The results are presented for different frames, namely the inverted V-brace frames and diagonal brace frames of 4-story structure as well as the 9-story structure. The beams and columns are designed from W-section library of AISC, and the BRB cores area ranges from about 10 square centimeters to 55 square centimeters. As you can see, the BRB core area gradually decreases from the lowest story to the highest story. Now, I'm going to describe the nonlinear analysis and results. The nonlinear analysis is conducted using Seismic structure program. To verify the steel material properties used for BRB and RL-BRB, the results of experimental tests conducted on short and normal BRBs are used. As can be seen in this slide, there is a good agreement between the numerical and experimental hysteresis curve. The analysis considers two major issues. The first one is the P delta effect, which is considered by adding a dummy column in the frame, and another one is the deterioration of moment-resisting elements. For the purpose of deterioration, the concentrated plasticity model titled as Modified Ibarra-Medina is used. The formulation proposed by Professor Lignos is used for calculating the MI-MCHI parameters. In this slide, I have selected a short clip of the nonlinear analysis of the 9-story building reduced length BRB diagonal brace frame. The analysis here is for the nonlinear time story, which is not addressed the analysis used in this paper, but can give a better sense of what is happening during a real earthquake. Here, the pushover capacity curve of the four-story structure is presented. By comparing the pushover curves, the following results can be obtained. The BRB with hinge connection has the minimum capacity, elastic stiffness, and post-elastic stiffness. Rigid connection increases the capacity of the structure while it does not seriously affect the post-elastic stiffness. The strength degradation occurs in the moment resisting frame as opposed to other structures. Reduced length BRBF increased the capacity of the structure without any steel consumption. Also in this slide, you can see the pushover curves of a 9-story building. The results of the comparison of the curves are: considering the braced beam frame action contribution can increase the capacity as the dual SMRF-BRB system. RL-BRB provides a constant sound value of post-elastic stiffness. Proper post-elastic stiffness of RL-BRB can accommodate better drift uniformity and prevent drift concentration. Rigid beam to column connection is susceptible to strength degradation in conventional BRB systems. There is no strength degradation in our BRB structures with rigid beam to column connection. Finally, the conclusions of this study are summarized as follows. Reducing the core length in the BRB can provide excellent post-elastic stiffness and improve the lateral stability of the structure without any change in the cross-sectional area of the cores and increasing the weight of steel. Reducing the core length in the BRB can provide better seismic performance in comparison to conventional BRB while decreasing the cost of production. Rigid beam to column connection can lead in strength degradation in higher drifts of conventional BRB structures, while no strength degradation occurs in reduced length BRB structures. The moment capacity of the braced beam can improve the ultimate capacity of the BRB frame structures. No significant differences was observed when comparing dual SMRF-BRB and the BRBF with moment resisting connections. And finally, due to the time limit considered for the presentation, I address only the major issues. For more details, you may refer to the paper in the proceeding. Thank you for your attention.